So the first of these is sort of an update on what Michel Lulé and I have been doing about differential endowment of magmatic ore deposit types. And we've worked mostly on nickel, as you know, more recently on chrome up in the Ring of Fire. And it turns out that when we were sort of thinking about some of the things that might affect this, we realized that it applied to a wider range of different ore deposit types. So just a second there. Yeah. So all of these deposits of those commodities I just showed are all hosted by mafic ultramafic rocks, typically intrusives, but not exclusively. And they're basically olivine, OPX, CPX, plage, cumulate rocks in most cases. The rocks are really common. They're all over the place, as we'll see, but most are only really weakly mineralized for reasons I'll explain in a second. And there's differential endowment on all scales, so craton to craton, all the way down to individual parts of individual units. I'm going to just a second, laser pointer. We're going to focus on some of the larger ones. I've got some comparator ones that we've been working on. We're not going to cover the whole world or anything, but we'll talk about that. But anyway, larger scale variations rather than the small ones, which is more a matter of sort of the local dynamics of the systems. These are the comparators I've decided to look at. Obviously, Abitibi-Wawa and Wabigoon, because those are parts of Middle Earth and the most work has gone into those. And we're comparing that with what we call the Bird River, Uchi, Oxford Stole, La Grande, Eastmain domain up in the north. And then I thought it was useful to throw in Circum-Superior because the nickel deposits are so important and because they lack all of these others. And of course, the Norseman-Wool Unibelt or the Eastern Goldfields terrain, whatever your preference is, in Western Australia. And I've thrown in, just for a couple of slides, the VMS, which might or might not be relevant. I think it tells you something about, heat flow and heat corridors and that sort of thing. Harold obviously knows much more about that than I do, and many of you. And orogenic gold, which of course is later and superimposed, and that's a cratonization sort of stage process, so probably less relevant. But you can see here, for example, that the most important deposits are over here. In these environments, at least, and the same would apply to Pichinga or Norilsk or something like that. They would be on here, but I haven't put those areas on. Eagle's Nest, as we'll see, is quite important. Not many nickel deposits in the Wabigoon, just some showings and prospects. The big ones now in the Abitibi-Wawa was something that have been uneconomic up until now and still aren't being mined, or the low-grade deposits where you've basically just upgraded the nickel that was originally in olivine. And then, there's lots of small deposits there. Chrome, there's some chromite at Shabanduan. There's a Shabanduan nickel mine, of course, an Inco mine for a long time. There's some chromite horizons there. But it's really a big deal in Bird River and particularly in the McFalls Lake area of the Ring of Fire. The only sort of economic PGE deposit in Canada, and one of only 3 really in the world that are important, is Lac des Îles, and that's over in the eastern part of the Wabigoon, so not really western Wabigoon, which is the area that I'd really like to compare most for reasons I'll explain later. The iron titanium vanadium, Lac Doré, at least in this area. There's others in Canada, of course, but in Abitibi-Wawa, there's a bit up in the Ring of Fire, and these other areas don't seem to have much, if any. Then, of course, the VMS better than I do. There are secular variations too. We've been compiling this for a contribution we're going to make to a paper that Bruno's working on. And you can see that the main deposits are associated with the Tisdale and Kidman Row groups in the Abitibi. There's gabbro-associated deposits in the Blake River. Montcalm's a good example. A komatiitic low Mg komatiitic or komatiitic basaltic hosted deposit in the Deloro and Grasse, and some more gabbroic deposits down here. But the main focus was down here. But this seems to be what it is worldwide, that wherever there's a range of mafic, ultramafic magmas, that it's the most magnesian ones that are mineralized. It's not clear why that should be the case. If you can take a basaltic magma and make a Norilsk, why can't you do that in the Archean? But obviously the dynamics were different in these areas than in the gabbros. Just a sort of a summary of the different types and some examples you'll be familiar with, and a breakdown of what we've decided is really the most important thing to know about your nickel deposit is what the host rock is. So there's really only one Sudbury, and it doesn't contain anything else that we know of in terms of mineralization. Layered intrusions, you can see the Bushveld here contains all four types. It's a classic and well, one of the most important ore deposit hosts in the world. The Great Dyke contains three of these types. Duluth is basically nickel with a little bit of PGE in the Sonju Lake intrusion. The Stillwater has chrome and PGE. And then we can go down the list here, and I won't read through all of them. These are some of the big iron, titanium, vanadium deposits worldwide: Panzhou in China, Lactio in Quebec, and Telnus in Norway. And then there's also nickel deposits in pipes, plugs, and stocks like Giant Mascot in BC or Lynn Lake in Manitoba, Shirahamu in China, and the Ivrea zone in Italy, which is really interesting. We'll talk a little bit about that in the next talk. And then there's all the ones that are basically, whatever small amounts of sulfides were kicking around in ophiolites and orogenic peridotite when they formed, and the same with chrome forming in those sorts of environments. And then north acidic massifs are really don't host much nickel except for this McNickel showing slash prospect in Quebec. There's lots more that I could fill in, but those are ones that seem to encapsulate it that you might have heard of. A little bit of igneous petrology. When you crystallize an ultramafic magma or mafic magma, it crystallizes chrome, aluminum, iron oxide first, basically chromite, and that'll be as we'll see in the lower part of the system. On its own, without adding any sulfide, it reaches sulfide saturation much later. This might happen about 20% MgO as a measure of fractionation in the magma, and this might happen at, say, 10% MgO. It reaches sulfide saturation, and almost every intrusion that differentiates that point has a little seam, and even ones you've just walked across and wonder what a little bit of rust is there, like in Monroe Township, the Center Hill complex. You can find a little rusty layer right in the middle of it. And then as the magma becomes more evolved, more iron rich, it reaches oxide saturation, iron, titanium, vanadium oxide, so ilmenobmagnetite. All of these, so the chromite, the sulfide, immiscible sulfide droplets, and small iron oxides segregate along cotectics with silicates. So they crystallize along with olivine and or pyroxene and or plagioclase. And the amount of silicate is much larger. It's 60 to 100 times larger. So that's not really obvious on some of the phase diagrams you may have seen in igneous petrology, but the amounts of these that normally come out are actually quite small. So 1 to 2% max. Larger amounts, if you want to make an ore deposit, then you need to interact with wall rocks or intercumulus liquids, do some magma mixing, or have changes in any of these parameters here to reduce the solubility, to make more of that phase come out, quote, suddenly, or at least all at the same time in the same place. You could also take those cotectic things that are coming out together, and you could segregate them physically via some sort of differential settling process, which the sort of physical process well, I'm searching for the word here. The physical process is, as industry would know, would be called lutriation. That's what I was searching for. And you can also dynamically upgrade those xenomelts. I mean, you could start with a sulfide xenomelt out of the wall rock that contains no nickel or PGEs or copper, and then you can upgrade it, or you can do the same with magnetite xenocrysts. And I'm not going to get into any of those sort of details. As I said, in layered intrusions, they're good systems to look at, you know, Bushveld, muskox, Great Dyke, and so forth. And if there's significant nickel copper PG mineralization, it's usually at the base. And sure, it came out early, but the reason it's at the base is because the country rocks contain sulfur. And so that's, you know, the Platte Reef and the Bushveld's a good example of that. It's really more richer in copper because of the composition of the magma. And then chromite in the lower zones, typically, if there's a PGE reef, it's typically in the middle someplace like the Merensky in the Bushveld or the JM reef in the Stillwater. And then the oxides are in upper layers like the main magnetite zone in the Bushveld. So like I said, noted earlier, the Bushveld complex contains all these, but most contain only some of them, and a lot don't contain any, like quite a lot. The textures are really interesting. I'm not really going to talk about them, but I'm going to point out the textures of all these deposits can be quite similar. I don't have any photos in here. I showed those last fall, but you can see interstitial intercumulus oxides that look for all the world like they crystallize from liquids, and that's been proposed by some people, but for lots of thermodynamic reasons and so forth, it's really not thought to be a good, you know, that's reasonable. The chromite's different because the chromite occurs as lots of interstitial small crystals, but in the case of the iron oxides, for example, most people argue that there's some sort of recrystallization process that happens. And we're missing some of the really classic types of ores that we see in sulfides, you know, liquid sulfides, for example, breccia semi-massive and emulsive. So the implication is there weren't any oxide melts. If we look at intrusions, mafic, ultramafic intrusions across the Superior, so this was compiled by Michel and Jean Bedard, I believe, and in a report that we put out in 2020, you can see there's lots of mafic and ultramafic intrusions. So there's no shortage of, quote, perspective of intrusions. There's the komatiitic ones in the purple, and even they're pretty well spread out. There's quite a few of them. But it turns out very few of those are mineralized. So this is the mineralization now. The red stars are the nickel deposits, nickel copper PGE. The black ornamented symbols, basically deposits and diamonds and little circles for prospects or occurrences in all these commodities. The black ones are chromite, so there's the ring of fire up there. And you can see there's hardly any chromite in the Abitibi. And then iron oxides are in this purple, originally gray in the diagram, but I added those. So very sparsely and unevenly distributed. We can look at that in terms of some bar graphs. This is the nickel in kilotons. This includes Dumont and Crawford, which are gigantic, but super low grade. If we look at this one, which is probably more representative, you can see that the Abitibi's got more than the Wawa, which has more than some of these other terrains. The identifications of these are over here, but they're, you know, Opotica and Western Wabagoon and so forth are here. Something that's quite interesting is that Eagle's Nest, the deposit up in the Ring of Fire, it's a quite nice deposit. I mean, it's not even in the realm of Sudbury, and might be a lot of money spent putting a road up someplace where you can get nickel someplace else, but there's other reasons for building roads, and there's also quite a like a super giant nickel deposit or a chrome deposit up there. But Eagle's Nest is actually quite significant. Here's the chrome. You can see it's all basically in the North Caribou terrain. So in particular, the Ring of Fire intrusive suite, Big Trout Lake has quite a lot of chrome. Bit at Bird River. And then this is the titanium and vanadium, mostly in the Lac Doré complex and the Belle River complex. And then same for vanadium. I mean, not all report vanadium resources. So we've talked about that. So what controls what makes a nickel deposit and what might be varying then that affects the endowment? And that all nickel deposits require high degree partial melting of the mantle because you need to generate a sulfide undersaturated magma, and which doesn't take that much. But that's why we see it in a range from, basaltic compositions in the case of Norilsk to ultramafic. The things that I think are affecting the endowment more than anything are the density and the stress conditions that favor high magma flux. And we'll talk more about this, but crustal rifts more than craton margins, more, this is empirical, than translithospheric faults and much greater than in orogenic belts where you might just get some trans-extensional zones within an overall compressive area. And then having channelized magma lava pathways, and that applies to getting it up, but mainly at the side of making the ore deposit. So there are lots of opportunities for that to vary. Source of external sulfur, you need traps for the sulfides afterwards, and you need to preserve them, but we'll talk about that. Chrome, you don't need to meld it quite as much. And in fact, there's a peak in chrome at sort of about 20% MgO, and then it declines from there as chromite crystallizes. And it declines at more magnesian magmas because basically it's building up while olivine is crystallizing, and there's not much chrome in olivine. You need to pond the magma in the crust if you're going to put it into some kind of intrusion. And there's some variants there that we talked about. So the ones in orogenic peridotite. So those are basically forming as part of the ocean crust, the lower or upper mantle, basically, of the whole ocean floor system. Large differentiated intrusions, and of course now a more recognized type in basically magma conduits rather than large layered intrusions. Black Thor in the Ring of Fire would be a good example of that. Kemi in Finland, Railway Block in Zimbabwe. The platinum group's sort of similar. Same with the melting. You just need to make sure you melt all the sulfide in the mantle, which happens at about, say, 10% MgO. Also in orogenic peridotites, differentiated intrusions, but also in small intrusions with magmatic breccias. I'm not going to talk about those because that's a pretty local thing, but Lac des Îles and in Ontario and Vengaki in China would be good examples of those. And then the iron, titanium, vanadium, I'm still learning about that. I've worked on Penjoa a bit, and basically it's in those types of intrusions or in orogenic massifs also, and there's several different flavors of that, and there's a whole menu of different processes that people have invoked. That's probably the least well understood of all the ore deposit types. I should mention that the model for nickel deposits itself is probably the best of any ore deposit type. I think there's a lot more unknowns in other ore deposit types, but that doesn't extend to chrome or iron titanium oxide. And well, PGEs are pretty straightforward. It's just that it takes unique situations. So just a little bit more about magma flux. So you obviously need large volumes of magma. So plumes are good. So having komatiites around or picrites is good. And that's much better than, say, a mid-ocean ridge type magma. High tension, I think that is important for reasons I'll explain in a bit, and high buoyancy. So Most magmas are less dense than the crust, but obviously a lot of them don't get all the way up. So that depends partly on the density of the crust. And so a denser crust allows magmas to come up more rapidly. And I think that has affected part of the difference between what we find in the Abitibi and what's in the Eastern Goldfields. Other things are viscosity, which has an effect, but not as much. Crustal strength, and there's always that, but some sort of subvertical transcrustal suture fault used to be important. I think, that might still be. This craton margin thing is sort of taken over, but I think actually tension's the key thing. And then a variety of other things. So what controls that? Well, like I mentioned, tension, crustal density, lithospheric thickness I mentioned. We talked a little bit about volume. I'll just mention here a little bit about intervals between eruptive events. Like I said, density and viscosity. So basaltic magmas are less dense than komatiitic magmas, and komatiitic magmas are less viscous than these. But that's not absolutely critical because we form at least nickel deposits in all of those, that entire range. Channelization is important. This is sort of different, it's for a different purpose from this paper, but I like the diagram. And the idea is that you can have a sort of a dimensionless frequency of intrusion, and whether or not the dikes come up over a spread of time and each cools before the next one comes up, in which case that one doesn't know that there was a dike there. In this case, this dike here knew that these others were there and that they were still hot, and this was an area of focused heat, so good for making a VMS deposit maybe. And here, everything comes up the one channel. So you get everything coming up to, or you get a number of these spread out depending on the scale to feed a single volcano or intrusion. So this is preferable because that means all the heat is there and anything that needs to be transported is going to be transported more easily than all these thin dikes, which almost never contain any mineralization. The effective density, this is a slightly different model. I didn't have time to prepare one for this talk. This is one we did for the Thompson Nickel Belt. And this just shows the effect of bulk density shown here in blue in both diagrams. This is where the sulfide facies iron formation contain 10% water, and this is where they don't contain any water. In other words, they're already consolidated, maybe even metamorphosed. And you can see that affects the density quite a lot. And there's little subsidiary kicks here below the iron formations, and we think that's why the intrusions were intruded mostly around these. It could be just a rheology thing too, but we think it might have something of density too. But that applies here, is that a denser magma or a magma containing sulfide is going to have an easier time getting up when the bulk density of the whole crust, so all of this, the lower crust and the upper crust is greater. So a little bit of an interpretive summary here, and I'm hoping, and I guess I should probably be there. I've come to a couple of these meetings, but is to get information to help me think about this. So the Abitibi is mostly Neo-Archean. It's very juvenile crust. There aren't very many inherited zircons. So the idea is that maybe that was relatively low density crust compared to some of the others. I think the thoughts might be the same about the Wabigoon. I'm less sure about that, just what I've read. We don't know much about the Byoji, or however Michelle pronounces it, except that there's a lot of Mesoarchean around too, so maybe it's higher density. The Circumsuperior is Proterozoic, but had Archean underneath it, so that's older and presumably already metamorphosed, and so that could have been quite higher density in the underlying crust before that got shoved over as a clippa. And then the Norseman Wool Unibelt, well, it definitely has Mesoarchean. They've done quite a lot of work there. So David Mole, for example, is that. The ultramafic magma is not so critical, whether it's volcanic or subvolcanic, not so critical, although the komatiites in the Wabagoon are mostly volcaniclastic, so that's telling us something about the eruptibility of the magma. Tectonic setting, I have no idea about these. I think we have a pretty good idea here about this being a rifted margin. I'm pretty confident of that, and there's, you know, Wouter Bleecker and people like that would, and Mark St. Onge and Andrew Hines would, or were the ones that originally proposed that. And then I think there's a good idea now that the Norseman Woyuna is a continental rift along a suture and step, so that there's actually, you know, two ages, something much younger here that's through the eastern goldfields, I guess. And then if we look at it in cross section, that this part's actually thicker than that. You know, the argument is that a plume came up and got directed toward that. But I think the key thing is that there's lots of evidence that the whole Norseman Woyuna belt was actually rifting at the time. That's work by me and David Groves and Warren Badd about like 30 years ago. So I think it's a continental rift first, and that happened and was focused along a suture and step. And so, you know, some of that craton margin model for the magma, the plume coming up is fine, but I think it's the tension that's critical. So I think that the magma ascent and eruption and flow velocities were much greater, or intrusion velocities were much greater in Norseman Woyuna than in the Abitibi. Yeah, so that's about it. So I need your help on that, sort of helping to populate this and think about that, and maybe we can come up, you know, add some other parts of the Abitibi on there, you know, where there are magmatic ore deposits. In terms of prospectivity, I'll just sort of wrap back around. I think that, in fact, the grouping we've got here, where nickel is basically in Sudbury, because it's, well, in effect, it melted nickel that was in the Nipissing and the East Bull Lake complexes, which formed during the Proterozoic, and just gobbled those up. But magma conduits are the place to look for that, and that's because the magma flux is the highest. That's the most channelized of all these environments. Layered intrusions, whether they're replenished like the Bushveld or composite like Duluth, have much less sulfide associated with them. There's some, especially at Duluth, but and you know, there's the Platte Reef, for example, and well, it's really a PGE deposit. Anyway, these have more intermediate magma flux. These orogenic peridotites, the you know, fairly low to intermediate flux, you can form chromite that way, but sulfides you don't tend to form very much. And those basically need to be upgraded through laterization to make them economic. So that's about all I've got. Like I said, we need, Michelle and I need some help on sort of thinking about this, and that's what we're hoping to get from working with Bruno and gang on the time slice paper and other things. I don't know if there are any questions.
You hear us?
Yeah.